deep learning and disease definition. It is my privilege to introduce Professor Arup Kumar Pal, currently serving as an associate professor in the Department of Computer Science and Engineering at IIT Dhanbad. Professor Pal received his B.Tech in Computer Science and Engineering from the Government College of Engineering and Textile Technology, Behrampur in 2006 and his PhD from IIT Dhanbad in 2011. Earlier in his career, he also served as a lecturer in NIT Jamshedpur with over 14 years of teaching and research experience. Professor Paul has published more than 100 research papers in reputed journals and international conferences. He has successfully guided 12 PhD scholars with significant contributions in information security, image security, data hiding, blockchain, and DNA computing. He has received several Best Paper Awards, completed prestigious R&D projects funded by ICMR, DHT, CSIR, and C3I Hub, IIT Kanpur, and actively contribute as a committee member in the various conferences and workshops. His core research interests including information security, blockchain, multimedia security, and image analysis. We are truly honored to have him with us today, and I warmly welcome Professor Paul to deliver his expert talk. The session is yours, sir.
Good evening to all of you. Thank you, Abhishek, for your introductions. Thank you, Dr. Pravir, for inviting me for presenting my lecture in this particular options. So let me share my lecture notes. Just a minute. So is it visible?
Yes, sir.
Is it visible? No.
Yes,
Hello.
sir.
Okay. Thank you. So today I basically talk about the image analysis using the deep learning mechanism. So today basically my main concern will be the content-based medical image retrieval topics. Okay, so that will be my main concern. So this is the outline of my presentation. So here we basically talk about content-based medical image retrieval, and also we basically see what are the mechanism we basically follow in this particular process, what are the ML and DL feature, because in this particular process the feature extraction is basically one of the major concern. So that particular topics we basically learn, and also what is the advantage whenever you talk about the DL, and at the same times what are the challenges we basically face, because whenever we are learning with the whenever you are dealing with the medical data, the main concern is that the less amount of data. So there we basically talk about the transfer learning. That is another way to train the data, and there we basically talk about two mechanisms. One is the feature extraction versus fine tuning. So which one is basically gives the better way to extract the better solution. So this way we basically give the outline of our today's lectures. So what is objective? The objective of a medical image analysis is that to extract the meaningful information that basically help us for diagnosis process, even the proper treatment planning, and even in the what will be the proper treatment process will be there. So that will be the that is the proper objective behind the medical image analysis. Now, in the conventional medical image analysis, what is the practice? Now, we basically takes the medical digital data, and the expert basically examine the data manually, and basis on that, they basically give the feedback. But the expert manpower is basically limited in the real scenario. So where there is a requirement how we can make these things automatic. So that is the one of the major concern. So in this particular aspect, deep learning basically becomes a promising research area where how this deep learning based mechanism can analyze these medical images in a automatic way. So that is the major concern. So the main the success of machine learning basically depends on the extraction of the suitable and meaningful data from the medical data, and here the expert knowledge is also required. But in case of whenever you talk about the DL, that DL basically perform these things in an automatic way, and it basically extract the things from the raw data through the different kind of learning mechanisms, and it basically gives more informative data compared to the machine learning techniques. So that is the basic advantage whenever you talk about the ML-based mechanisms. Okay, so what is the things? Now we can see that PAC is one of the standard mechanisms which is used in a worldwide, which to manage the hospital management systems, and they basically deals with a large volume of medical data, and this data is basically in a petabyte, means the size of this data is basically petabyte. Okay, means 1 petabyte is 1024 terabytes. So that is a huge volume, and the nature of this data is more complex. Yes or no? So what sometimes the data may be in the X-ray, it may be CT scan, it may be MRI, it may be PET. So there may be different kind of modalities may be there. I'll discuss what are the modalities is used in the medical imaging in the later. But in the medical imaging, so there is a lot of medical imaging is there, and this medical imaging have a lot of modalities. So we need certain mechanism. Those mechanism can handle this kind of image modalities. From there, they can extract meaningful informative analysis data, so that it can give some clinical diagnostics outcome. Because the manual diagnosis may be sometimes error prone, but the automatic diagnosis can give some quick response, and sometimes where the expert is not available, and that cases this kind of practices is quite effective. So that's why you can see that the government of India also taken some initiative how to develop some AI-based medical resources so that we can basically replace those kind of demand of this expertise in case of, because initial level we can keep the initial solution based on the AI-based technology. Okay, so this is the basically deals with the patient specific, and it basically deals with a more drastic way compared to the conventional way. That means it basically beyonds on the more generic, and it basically gives some more details of the what kind of possibility is there, what kind of possibility, what are the possible treatment may be possible. This kind of more details means it can give more details so it can provide the solution. So whenever we consider the diagnostic approach, traditionally relied on physicians' accumulated experience, recalling similar cases from memory to inform a new diagnosis. But in large searchable images, archive could make this process easier to the expertise, so that they can get the more relevant case studies, and basis on this case study, they can take the necessary steps for the treatment process. So here the image retrieval may be one of the great solution. So now in this particular retrieval process, I want to show you that traditional retrieval process, there is a two types of mechanism is there. One mechanism is basically called as a uh, text-based retrieval process. So what is the text-based retrieval process? Now, say for example, you have a given one patient records. A patient record is basically stored with the patient name and patient ID like this. So whenever you are giving this patient ID and patient name, you are basically retrieving that particular patient ID and patient CT scan or X-ray data, and you can visualize these things and you are getting these things. But as a expertise, suppose I know that that some patient having this kind of condition and they have given this kind of treatment. But with the help of this text information, that means if I say that which patient, it is quite difficult to remember all those things. So that means the text-based retrieval process is not quite suitable in the real-time scenario, basically in medical science, because medical science it is not quite feasible to remember which patient's case study corresponding you have to remember it. So that means uh, here there is another mechanism is also there, that is called the image based searching process, and another text based retrieval searching process. And generally basically talk about like a file name, keyword, location, and this kind of information we basically provide to retrieve the content. Okay, so there is another limitation of a text-based retrieval searching process. Suppose you want to express this particular image. So somebody says that it is a horse, somebody says that it is the image of forest, somebody says that it is the image of grass, tree. So so many people can give the tag according to this. The same things happened with the medical imaging. So medical imaging, a particular image can be represented by the different nomenclature. Yes or no? So that means that way, if you want to search, then it is quite difficult to get the meaningful things. That means the TBR process is basically have seven limitation. The major limitation is that so if you have a large data size, so then the tagging is basically tedious process. The database annotation is basically one of the tedious process. That means each and every database you have to manually you have to tag it. So sometimes this tagging is not a correct. That is called the wrong human perception may be occurred in this particular process. Sometimes you can give the wrong keyword. The correct keyword is not associated. So that means it basically the whole process may be continuously, it may be the goes wrong, and at the same time this whole process may be the tedious. So that is one of the challenge in this particular process. So here we can see that the content-based image retrieval, that is one of the popular terminology. So what is the content-based image retrieval? Now we basically search the content with the based on the actual content rather than the giving the content of the giving the actual tagging value. So say for example, suppose they are giving the query image, and based on this query image, we basically extract some feature. Already, I basically perform the similarity matching with respect to this feature, and basis on that, those having the similar features, those similar images can be retrieved in this particular process. So similar way, if the medical imaging, if you have some similar medical query image in terms of medical image, I basically retrieve the similar medical images, and from there I can retrieve the case study of the corresponding patient. So that way we can deal with the medical imaging. So that means content-based medical image retrieval. So that is the way I can deal with. So what is the general framework? So in terms of a content-based image retrieval, so there is one will be the content on it. That means a hospital basically generate the medical images, and from these medical images, we basically generate features, and that features will be stored in an image repository. For that means every image corresponding will basically generate a feature vector, and that feature vector dimension is quite less compared to the original image, because the straightforward comparison is not a more suitable. So rather than comparing the straightforward, we basically find out the most salient component, more salient component of the image, that is called the feature vector. And now the similar way, we basically takes the image, and from there we basically extract the image, that is the feature extract, and we perform the similarity measures, and after that we basically based on the distance measure, we basically give the retrieve images. So this particular process can be realized. This diagram basically shows that how the content-based image retrieval system works. Okay, so it basically works in two phases. That is offline mode, and another is the online mode. So in the offline phase, the retrieve database is processed by extracting the visual feature, that is color, texture, shape, or sometimes deep learning based descriptor from each image. And these features are organized into an efficient database index to enable fast searching. In the online phase, a user provides a query image, and the system extract is featured in the same manner as the database images. Then what happened? The query feature are then compared with the index database feature using the similar measures. The similarity measures, we can use the suitable distance measure like Euclidean distance measure like marathon distance, all those things. Then images are scored or ranked based on their closeness to the query. A ranking step may be applied to the initial result through the relevance feedback or semantic analysis, ensuring better accuracy. Finally, the system returns a list of retrieved results, displaying the results. Those are most similar to the query image. So that is basically occurred in a two phase. So that means offline phase, this is the most huge computation over it, but this online phase has not that much. That is it can move in a quite faster manner. So that means this step is tedious, but this step is not that much tedious. Okay, so retrieval process is very fast because already the feature vector is stored in the feature database. So based on this these major steps of this severe process can be categorized in the four steps. First step is the feature extraction. That means we have to extract the salient component. That salient component may be in terms of a handcrafted features or maybe the deep features. Okay, and naturally in this particular session, we basically show you how the deep features can be used to extract these particular things. But both the way you can extract the feature. And after these things, we basically extra feature vectors will be stored in the database, and that will be considered as a feature database, and that will be used to similarity measurement process in the later stage. And in the similarity measurements, we basically use the same query feature vector, which is taken from the query image in online mode. So that these two basically done in the offline phase, and this is basically done in the online phase. And here the similarity measure is basically carried out. And after that, all the distance measures, based on the distance measures, the relevant images has been displayed, which are more close to the query image. Say, for example, suppose you have a query image, this one, and according to the feature vector, we basically perform the similarity matchings, and according to the similarity matching, we basically retrieve all the X-ray images. Those are close to these particular images. Okay. Now, in generally, there is a handcrafted features is basically used for this particular process. There is a three types of handcrafted features are basically used. One is called the color features. Another is the texture features. And another is the shape feature. And sometimes we basically consider the combination of these three in a proper way to design more suitable CBR process. Now, in severe process, one of the big challenge is the semantic gap problem. So what is the semantic gap problems? Now, semantic gap problem means actually what is machine is perception and what is human being is perception. Because sometimes these two images as a human being, we can say that both images belongs to the same category. But machine perception, they basically sees that both may not be the same category, because here the background content is more compared to the foreground. Yes or no? So human perception, both the image content are same, but the machine perception both are not the same. So that is one of the big challenge. Like there is another problem here. Like this is the one of the component. This particular image for the machine perception, we can see that it may be the apple. Somebody says no, it may be the guava. According to the machine perception, we can retrieve a different kind of structure. Means if you follow the structure, then you can get a different kind of structure outcome. If you follow the color, if you follow the structure, you'll get that. If you restrict the color, then you'll get that restricted outcome. So that means the machine cannot be understand whatever the human being can be understand. So that is the one of the semantic gap problem is there. So here deep learning basically deep learning, which is basically particularly convolutional neural network, is basically play an important role. Instead of considering the handcrafted features, deep learning models, which is capable automatically learning a hierarchy of increasing complex and abstract feature directly from the raw pixels. And this ability representation from data that is more important to develop more robust systems. And these particular systems basically achieve the feature in a different level, like a low-level features. Sometimes it may be the mid-level features. It may be the high-level features. Now, under the low-level features, we basically see the basic structure, like it may be the edge, it may be the color, it may be the gradient, like this. Whenever we talk about the mid-level features, we basically see the combination of edge and texture, or sometimes we basically see more complex representation of the low level features. So that basically more suitable whenever talk about the pathological or medical content analysis process. So mid-level feature basically play an important role. And another is the highest level. So this basically at this stage, yeah, we basically takes more relevant structure, like a, what is the tumor structure, what may be the means what may be the category of the structure, means a more detailed structure of these particular things may be acquired in this particular high level structure. So the deep learning basically gives the more informative content in different hierarchical levels. So that is the more advantageous compared to the handcrafted vision. So if we compare with respect to machine learning, if we consider with respect to machine learning to deep learning, so we have basically compared with respect like text-based retrieval. Another is the traditional content-based image retrieval, and is the deep learning-based hello. Hello, can you hear me?
Yes,
Yes,
sir.
sir.
Yes, yes. Sorry, some technical issue. Okay. So, whenever talk about the deep learning, so it basically having the basically three level of features, like a low level features and mid level features and high level features. And these particular features basically helps us to develop a most robust diagnostic systems. Okay, that basically to more suitable to analyze like a medical imaging like X-ray images or CT scan images or or all those images. Okay, so so here if we see these particular things, that the traditional machine learning to deep learning is basically improvement of changing the solving a complex perception problem. Like means whatever we see in the conventional like a machine learning base, so that means handcrafted feature we basically see or knowledge of the expert is required. But in the deep learning, it basically learn from the pixel automatically so that it can design a robust system in this particular process. So that is the one of the advantage. So if we compare these particular things, so that is it is manual, traditional content-based images are semi-automated. That means we basically train the handcrafted feature, but it is basically fully automated. Yes or no? So definitely, sometimes the deep learning basically work as a black box, and but the thing is that the performance of deep learning has been seen more better than compared to the other approaches. Whenever you have a efficiently more number of data set is available, because data set is one of the very important whenever you are dealing with the deep learning based techniques. Okay, but in the medical imaging, this is the one of the major concerns. So that particular things I want to address in this particular lecture. So what kind of medical imaging modalities is there? Like X-ray, CT, MRI, or PET, or microscope. Those are basically used imaging techniques. Like X-ray are basically quick and mainly used for the bone or fracture or chest imaging. But whereas the CT scan basically combine multiple X-rays to produce cross sections images, provide detailed 3D views, bone tumors, or even some internal injuries through higher radiation may be possible in this particular process. Whereas the MRI basically uses the magnetic fields or radio waves to generate more detailing of these particular things to enhance the contrast. So that is the another way of representation. PET scan also another way of representation that basically sometimes is basically useful for the cancer treatment or brain or heart studies. Ultrasound also give the real-time radiation-free imagery commonly used in studies for the organ segmentation, motion tracking, or disease classification. Okay, like it may be the abdominal or cardiac vascular microscopy. It basically studies in case of microscopies, bioscopies, samples, all these things. So this is the different kind of modalities is there, and according to different modalities, there is so many medical imaging techniques is basically vast in this particular area. So this is another area like a dermatology. It is basically deals with the skin images. Fundus ophthalmology, so that means it is retinal images. It basically deals with retinal images. Endoscopy, dental imagings, nuclear medicine. So that is a lots of modalities is there, and there is a lot of research is going on in this particular area, so that we can develop a robust particular things. Now, whenever you talk about the deep learning with medical imagings, deep learning having uh, is very powerful at recognizing object, and also at the same time it is also more suitable for classification different categories. So in medical imaging, this detection as well as categorize of the abnormalities of the diseases is very, very important, and that can be effectively we can done using the deep learning algorithms. So now in this particular process, so there is this, what is the advantage? Now advantage is like that it basically supports automated feature extraction process. It means that automatically the system can learn, extract complex structure from the raw pixels to identify the patterns of the digits. That is the one of the major concern. Another thing is that it basically improve the diagnostic accuracy because deep learning techniques basically deals with a large amount of data. So naturally, its accuracy is quite high compared to the traditional mechanisms. And also, it enhances the image quality and reconstruction. So that means that deep learning based mechanisms can be used to enhance the image quality, means it can be used as a enhancement techniques process also. uh, that is another area that is also useful. That means because in the medical imaging, whole image content is not necessary for your study purpose. Uh, some subjective area is required for in your study purpose. So segmentation or localization is very, very important. So that means automated segmentation localization is basically is very, very important in this particular process. And there basically medical imaging can be segmented, or localization can be done using the help of DL-based mechanism. So, so here, this kind of application, these kind of operations can be achieved with the help of the large volume of medical data, uh, uh, with the large volume of medical maker, that makes the process more quite easy, and more and performance is quite high compared to the conventional practices. But the challenges are like this. The scarcity of annotated data, that is one of the challenges, because deep learning architecture basically requires use large label data, but sometimes due to the restrictions of the collection of the data, or sometimes there is so many restriction is there in for the collection of data. But if somebody have the data of the medical data, they are not able to share the data in the globally, because that is having some kind of restriction. That means we basically see that the data sharing is another challenge in this particular process. So scarcity is another issue in this particular cases. So how the scarcity of this data can be handled, and there we basically overcome this kind of problem through the annotation process. Another is the annotation cost, because sometimes whenever it takes the data, due to the expert knowledge is also required to annotate this particular data. So cost is also required in this particular process quite high in this particular process. We also received one project from the ICMR, and there the major funding is then given for the data creation and data annotation, rather than the development of this technology. So, five AIMS institute is there, along with the two national importance like NITs, one IITs is there. But major funding is given for the data creation and annotation process. So that is, annotation cost is very, very high in this particular process. And another challenge is that data quality. That means medical image, whenever you acquire, and that can be acquired in a different diverse imaging systems. And there may be the possible that image may not be consistent, and sometimes due to the presence of different kind of noise, image may be degraded. So we have to overcome this kind of scenario. So that means image restoration process is also required in this particular process. Another is the data bias, because imbalanced data set is one of the uh, bottleneck in the deep learning model. So that means whenever you want to train the things, bias data is data bias is also one of the challenge. That means imbalanced data set is not required in this particular process. Data privacy, that means sensitive nature of patient data should not be presence in the outside of the system. That means how the data should not be shared with the consent of the patient. So that is one of the big deal in this particular process. So this is the big challenge. So to solve this challenge, we basically see that we basically follow a different kind of patches mechanism. That means a large image is divided into small patches, and that patches is considered another images. And sometimes we basically use the data augmentation process. That means and the actual image is artificially transformed into another image, like a different kind of rotation, scaling, and flipping operation to generate a huge volume of data. That is called the data augmentation process. And that is a very important transfer learning, because transfer learning means already we are using the pre-trained networks that is already trained with the natural image data sets, and this data set will be used to train our medical data for getting our desired outcome. So how the transfer learning is more effective in this particular process, that particular things we basically see. Now, in medical imaging, two common strategy, that is deep learning, that is feature extraction and fine tuning, are basically used in this particular process. So the first strategy, that is feature extraction, it basically takes a pre-trained networks which is basically trained on a large data set, natural image data set like ImageNet, to generate a train networks that is basically effectively work on natural data set. And now we basically use this particular network to use the medical images without training the entire deep learning networks. So that is one of the objectives. So these extracted features, whenever you use these medical images, already the pre-trained networks, these extracted features can be integrated into existing image analysis pipeline, so which basically saves time as well as computational resources in the network layer. And another is the fine tuning. So fine tuning is what? Now it basically adopt a pre-trained networks, but here we basically adjust some learning features, like sometimes we basically tune these particular parameters based on this medical data, medical data to get the more desired outcome. So what is the way you can tune this data, tune the data that I basically want that I'll extract? So there is a two mechanism. One is the fine tuning mechanism. That means the existing networks will be tuned with respect to the medical data. That is the another way. So so what is the way? And we basically see that there is a two mechanism is basically used. Like suppose you are using the VGG16 networks. So in this particular cases, what happened? Now we basically use the freezing concept. So what is the freezing concept? Now some layer we basically freeze in this particular process, and some layer we basically unfreeze in this particular process. That means during the training process, the freeze layer will not update their weight value. Okay, and some layer will be updated, their weight value will be updated in this particular process. Okay, so this freezing concept will be used to train the networks. So this kind of approach basically helps to train the medical data in a more efficient way, and in a, because large already, because the small volume of data from the scratch, if you want to train, it will not give the good accuracy. So it is better to use the pre-trained networks, but don't disturb the network. So you freeze some basic layers, and but some layers you can train with respect to your using your medical data. So that is the thing. So that I basically want to give one demonstration how the freezing and unfreezing constant basically improve the performance of this medical image analysis process. So that basically wants to show you. So here this particular process, the fine-tuning process, this freezing and unfreezing process, whenever you have a particular content, that means that is you have a that this main core idea is like that. When the fine tuning, that top layer already it is top layer, it is basically huge computation over is required in this particular process. So this particular layer will not be touched. We basically touch those layer having not that much computation over it, and that particular layer we basically tune with respect to your data set, so that the overall computation not be increased, and the performance should not be degraded in this particular process. Okay, so what is the basic steps in this particular process? Now we basically take the input, we basically take the pre-trained networks, some bottom layer will be the frozen, and that basically extract some basic structure that is the common, and top layer will be the unfrozen, that basically used for specific tasks. So and this top layer will be trained with respect to your medical data, and these output features will be given to the new classifier for the train the data, and that will give the final outcome. So this particular process, so we can see that the fine-tuning strategy pre-trained network will be initiated. So first it will initiate a pre-trained convolution base, like a VGG16 weight value will be loaded, and then we add a custom classifier on the top, perform to specific tasks, so that what kind of operations we can see, whether it is a disease classification or not. So initially we freeze the convolution base to prevent the weight from the being updated, and train only the new classifier for the few epochs. So these steps allows the classifier lump stable initial weight without disturbing the general purpose feature in the base. Once the classifier is reasonably trained, we unfreeze a few of the top layer of the base model, those close of the output which capture the more task-specific pattern. Finally, we retain the model, which is unfrozen base layer and with very learning rate. So finally, we basically get some more accurate and more desirable results with respect to this particular process. So here we have given one demonstration. So my scholar, he will given one demonstration based on with respect to the VGG16. That is how the VGG16s can be used to capture the medical image in a transform learning approach, because the one of the major bottleneck of the medical imaging is that less amount of data. So how the less amount of data can be trained with the help of the transform learning, because the model can be changed, because our objective is how this approach can be used, so that the medical imaging, because the medical image is the major bottleneck is that we have the less amount of data. So how the less amount of data can be used to design a robust network. Okay, so so these particular things will be presented by my scholar. So let me finish my presentation, so then he'll present these particular things. So in this particular process, we basically see that that using the transfer learning process, we have basically want to see one's cancer data set. We basically use the one of the data set, skin data set we have taken, and that particular data sets having very less amount of data in some category. Okay, so to overcome these particular problems, we basically use different kind of augmentation approach to increase these data sets, like a flip horizontal, flip vertical like this. And after that, we can see that this particular data set has been accuracy has been increased in a certain category, but certain categories accuracy has not increased that much because the number of data sets is not that much presence in that particular process. Now, this is the some representative outcome where if you give this kind of input query image, and this is the corresponding outcome with respect to this query image. And this particular, this is the another outcome with respect to modified BGG16. And in this particular modification, we basically use a different optimizer to improve the performance of the conventional BGG16s. And here we have seen that that in every category, the accuracy has been drastically increased compared to the previous one. So that means whatever the accuracy was there, like in this particular cases, we have used the different optimizers so that learning rate can be decreased and we can achieve the more accuracy in this particular process. That is the more objective. So that means what is the our main concern? The main concern is that you have to use one more robust architectures. That architecture can be used in a transfer learning process so that you can achieve the desired outcome in this particular process. So what we have seen in this particular process, we have very small data. We have seen that whenever we are using a very small data set, there is a possibility that the training is very quite fast. We have only updated very few weight in this particular process. Computation, it is very cheap and it is effective even for the small data set. But the disadvantage is that it is very less flexible because it is not able to learn the feature when you have a more complex or more various medical imaging modalities in this particular process. So that is another demerit in this particular process. Another advantage is that it basically, compared to the fine tuning, it has basically having higher performance, like can achieve higher accuracy than feature extraction process, and it is basically more powerful compared to the more flexible than training knowledge, but computationally expensive, require more data, and basically if your data is too small, then it is not working in that much effective way. So that means overfitting problem may be occurred in this particular process also. So if we compare these things, so that means feature extraction process is quite fast, but fine tuning is basically slower. It because basically required data is basically more data is required in fine tuning process. Computation is quite high compared to the feature extraction process. Performance definitely is better in fine tuning process, but there is a risk of overfitting, and the main action is unfreezing, which layer is you have to unfreeze. That is the one of the major concern in this particular process. So here, let's see the choice between the feature extraction and fine tuning transfer depends mainly on two factors. That is size of the available data set and its similarity to the data set used for pre-training. So when dealing with a small data set that is similar to the source data set, feature extraction basically prefers strategy. So in this case, the pre-trained networks feature are already well suited to the stacks, and retrain the model through the fine-tuning make lead overfitting because the limited data. So if we have a large data set, then similar data fine-tuning becomes the best options. In the other case, when you have enough available data sets, in that case, the model can adopt its learned representation to the target domain more effectively, which often results in higher accuracy and stronger performance. It basically provides the stronger performance. For a small data set that is very different from the pre-trained data set, the situation is more challenging. So the pre-trained feature may not fully capture the new domain's characteristic, simple feature extraction from earlier layer. So the most reliable solution in this scenario is to acquire more level data to improve the learning, and which is one of the big challenge, because in the data set collection is very big challenge in this particular process. So when the working in the large data set, that is different from the source data set, fine tuning may many layers or even training a model from the scratch become feasible. So data proper data collection, that means the large data. So that means the data set size and signal guide the optimal strategy choice is very important. According that depends on your data set and what kind of problem statement you are working in this particular process. So that is one of the major concern. So deep learning is basically one of the very important tools, and definitely its performance basically solely depends on your data sets. And if you have a large volume of data, so definitely your performance is very improved drastically. So and at the same times, but the big challenge is that the data, because if somebody have the data, because the data sharing is not that much easier, because there is so many restriction is there in this particular process. So we have to think about different kind of alternate mechanism, so that with the help of the limited data, how can improve the performance using the like a fusing some local global features, or using some more advanced architectures like a Bayesian transform or hybrid models to improve the performance. Even the federated learning or ensured learning may be the one of the solution, where with the help of the federated learning and blockchain based mechanism can resolve the data sharing problem also, because in that case you no need to the big challenge of the data sharing can be overcome if you consider the federated learning along with the blockchain. So that means these strategies also overcome this particular limitation. So this definitely the performance of the machine deep learning solely depends on the huge volume of trusted data, and this can be achieved whenever you have a huge volume of data, and other than you have to think about some alternate mechanism. So now I'll request my scholar Sukla to present how the transfer learning can be more effective solution to achieve the desired solution whenever you have a less amount of data sets. Okay, so Sukla,
Okay.
please.
Okay, thank you, sir. Now, let me just present. So in this particular notebook, through this Colab notebook, we will just see how a particular backbone network, let's say your VGG-Net16, in this example we have taken, how we can extract the pretend features and we can utilize further for your medical research. Now, why this important to use any transfer learning backbone networks, as sir has already discussed. I will just show how these features are here shown. That means how the transfer learning or the pretend features, if we extract the pretend features, then how it can be visualized, how the features are learned, or the weight matrices are getting activated onto the raw pixels. That we will just show and compare with the simple scene in architecture, how it is distinguished with the pretend features as well as the traditional convolutional features. Okay.
Data to a central server for analysis.
Okay, so let me connect my notebook. So here I've just taken one particular sample image, and we will just see how this pretend features is getting, activated weights are getting visualized in that particular input image with the pretend features, as well as what are the features being learned with a simple CNN architecture without training this CNN architecture, as well as without fine tuning the backbone networks, right? You can use any backbone networks in your case, if in your medical data, whether you can use VGGNet, whether you use ResNet 50 or EfficientNet or any vision transformer models, that's no issue. But in case you have, in case of this particular, in case of this particular demonstration, we just show this how this base model, that means we have just downloaded the pretent weights, that is the VGG 16, right? And we have got this particular input image, right? This skin lesions to detect if any cancer cells is present or not. That is already present in the data set, right? That is already cited in the particular slides Sarah has already shown. So we'll just visualize through these particular plot functions how the feature maps are getting activated through the pretent networks, right? So we just, if you go through the particular architecture of this particular VGG net architecture, you see there are two convolution layers. That means in this particular block, let's say there are 5 blocks, right? Block 1, block 2, block 3, 4, and 5. And the first 2 blocks has 2 convolution layers, right? And in between there, we have the max pooling to reduce the spatial dimensionality. And again, we have these 3 convolutional layers 3 times. That means block 3, block 4, and block 5 has the 3 convolution layers each. And why these convolution layers, number is not, is not set. It is optimized in their paper. This particular works best performance in the ImageNet data set, right? And finally, we'll have the fully connected layer, which is known as the classification part. So what are the feature extraction part? After this block 5, right? Block 1 to block 5 is your classification or feature extraction part, right? The features are getting fine-tuned here in each of these blocks. And next, we have this fully connected layer for your classification. Here, 1 cross 1 cross 1000. 1000 means your 1000 ImageNet classes are there. And if you have the 2 classes, then you will have 2 class here, 3 class problems, any of the class problems according to your disease classification or the segmentations, it will accordingly, it will be adjusted, right? In your model, the top layers, that means your fully connected layers, right? So from this particular block 1, that means the initial layers, block 1, block 2, how the feature getting, feature maps getting activated through the weight matrices, the pretent weights. Pretent networks means you have the pretent weights that is trained on the ImageNet data sets, right? And how these weights can be utilized for this transfer learning concept for a new data set, for example, your medical data sets that are smaller in size, these pretent weights will be very much useful because you don't need to learn anything about the natural images or images in particular, right? So this is the similar block architecture in different way. So the convolution layers are the first 5 blocks, right? 5 blocks. And initial layers are the block 1, block 2, and the mid layers you may consider block 3, block 4, and the more abstract representation of the layers are given in the block 5 in the VGGNet architecture. In any of the architecture, whether it is EfficientNet or any other DenseNet or ResNet or vision transformer, you will have different issues, but the similar feature extraction layers will be there, right? They have optimized their computational in terms of computational efficiency, in terms of their multiplications of the operations. They have reduced in their paper. That is a different issue. And then finally, we have the fully connected layer for the classifications. And the output layer, if you have any number of classes, that is the it will show, right? So with this VGGNet, you can replace it with any other architecture, no issue. But how the pretent architecture works. So if we run this particular block, see, we are seeing only the block 1, block 3, and block 5. After these 3 blocks, what are the feature maps that getting highlighted? See, according to this particular architecture, block 1 has the 64 filters, and block 3 will have the 256 filter. Here in this architecture, you can show the dimension already, the output dimension already given. the 64, 128, then in block 3, 256 dimension will be there, and block 4, 512, and block 5 will have 512 again, right? These are the filter maps. What are these filter maps? It's basically a weight matrices. This weight matrix and bias are called the parameters, number of parameters, right? So here, in this case, if we run this particular block, if you want to visualize this block 1 and block 2, block 3 and block 5, the intermediate blocks, initial to the final blocks of the VGGNet algorithm, you see that for this input image, if we activate the GradCam, or if the particular pixels getting through this weight matrix, the 64 filters, whether it is for in case of block 1, then we will see this 64 feature maps, right? For this particular, in each of these filters, we'll have different visualization, different feature learning, right? And because it is a pre-trained network, that means here in this case, the base model we have set is trainable. The base model dot trainable. That means VGG16 model dot trainable is set to false. That means we have freeze this particular convolutional base. That means the whatever the weight matrices is learned, that is now fixed. That is the static right now, right? It will not learn anything. Whatever the learned through the ImageNet, that particular weight matrices are getting fixed here. And through these weight matrices, we are just activating what are the low-level features, whether it is textures, any color gradient, or any other getting activated. Blue, darker blue means nothing is getting learned, and more of the highlighted in the yellowish, that means the weight matrices are more in this particular pixels, right? So here 64 feature maps there, and we can see that the some of the feature filters and able to learn correctly visualize or whatever at the low levels they are trying to activate these feature maps, right? Now if you try to visualize the block 3 here are the block 3. That means we have gone too far. That means initial levels we have is the block 1, and we have seen the low level features, textures, color gradients, or any types of low level features are getting highlighted here. And the more we go towards more deeper layers, that means here in the block 3, we can see the more abstract representation of the feature maps, right? More abstract representation of the feature map. Though these are the static, the whatever learned from the ImageNet features, right? We have frozen the pretend weights. So here, that's again the 256. I think for this block 3 output of this VGGNet blocks, right? So here 256 more abstract representation is shown in this particular because the train already trained on the ImageNet, right? And again, if we plot this block 5, that means the final block of the VGGNet, that the representation here is more abstract. That is not possible, cannot be achieved with the traditional handcrafted machine learning features. This more abstract representation only machine can interpret, right? And these are the abstract representation of the final layer, right? And how these are the 512, I think these are the 512 filter maps, right? We can see the more abstract representation of the all of these filter maps, right? Now, if we want to fine tune this particular frozen initial layers, fine tune means you are just freezing out the initial layers, and at the final convolution blocks or the block, you are just training the final top layers of your model, right? Top layers of your model. And now several research are already done that we need these low-level features, the intermediate level features, all as well as the more abstract level features, right? So we can combine these intermediate features also to make our final feature output. That is also done in several research or medical imaging process, right? So in the fine-tuning, what we just save the pretend weights and reload it. And here we just set the initial layers are the frozen, that means the trainable is false. And we set the trainable only the final layer, the final block in case of trainable is true. That's it. right? And here, this will be the particular VGG16 architecture. In the block 5, the 3 convolution, right? There will be here non-trainables, total trainable parameters is 0. Why? Because we have already frozen these trainable parameters. So those are all non-trainable. That means static weighted features, right? And here the similar things will happen. We can see the feature maps in every run. If I run this particular cell every time, the block 1, block 3 will give the same feature maps, right? But the block file will, it will again and again, it will give different outcomes with this block file, the more abstract representation. In that particular layer, we will train here in this block 5 layer, we will train again and again with our new data set, with our medical, any modalities of the medical image we have present, right? So in case of smaller kind of data sets, we have this advantages of the transfer learning. In any of the other data sets also, if you have more number of data sets also, in that case also, these pretent features are very much effective to get the more improved accuracies or precisions, right? So if you want to, if you just give the simple CNN architecture, just like just one convolution, there are 3 convolution layers. In between, there are max pooling layer, right? And if we just visualize these 3 convolution, right, with the same image, see, these are the initial level, the first convolution, the second convolution, and third convolution. But these are not as good as the learning for the pretent weights, right? These are still, after this last layer of the convolution, still these are not abstract, right? The abstract, we need more number of convolution in that case, right? But we achieved through this VGGNet pretent weights already with the block 5. That is the main advantage here. So the final conclusion will be that VGG16 maps, we with the pretent weights, we extract the low level features as well as the abstract level features. And in this simple CNN maps, if you untrained version of this simple CNN, we will have random filters, noisy blobs, we'll see in this case, right? So through training, more number of training epochs will be required in case of this, if we start from this scratch. And in the pretent networks, we can have lesser, more improved features, improved performance in case of this. Now, further research for any, if you want to do any further research, you can replace with this base networks with the recent any state of the art, let's say EfficientNet, any base version of the EfficientNet, and you can extract each of these blocks, right? And you can process with the segmentation task in the fully connected. You just paste, you can implement the pixel-wise loss functions here with the ground truths or the annotated levels, right? Small amount of data, you have the annotated levels. There is not available large amount of annotated data available due to the manpower and all those expertise requires, right? So in that case, the segmentation and localization tasks also be performed. And accordingly, you have to fine tune the features, right? That means in intermediate features, you can fuse intermediate features, you can fuse with other local and global perspective. You can do it, you can train differently, you can train, let's say, in a local manner or in a federated learning way, right? With the small data sets, and you combine them in a central repository, right? So there are a lot of scope in this particular domain, and according to your data, whatever you want to perform, whether it is segmentation or classification, based on your data, your architecture should be accordingly developed. The same architecture will not give the best performance. You have to enhance the feature extraction process or the fusion mechanisms so that you get the improved performance. So that's all for this demonstration. I hope things are clear.
Okay, so any questions?
Yes, sir, I have a question. Sir, I have 3 class of images. Each class I am having 100 set of images, sir. 100 images I am having. Is it possible to do image classification with 300 images in total? Each class 100 images.
Okay, so actually, you can perform the classification task, no issue, but you have to use the transfer learning as your data set is very much lower. We need more data to learn a particular deep learning model from scratch. So you can use the transfer learning, you can use the pre-trained networks, any of the pre-trained networks, right? And you can check for yourself which pre-trained network is working fine with your new data, and accordingly, your fully collected layer will be set to your 3 class, right? And then retrain your model. But before retraining, you can also check if your classification, that means your data, can be augmented further with the, just as sir has shown in the slide, if you can augment the data further with the all the augmentation mechanisms, right? You can do it in a 300 to 3000 by doing all the augmentation, right? You can also perform the augmentation, and you can definitely your work will be done, no issue, right?
Okay, sir. Sir, in augmentation,
Actually, generally 10,000 images required for any kind of application. So if
okay,
it is
okay,
hundreds,
sir.
it is quite difficult.
Okay, sir.
Okay, so
Actually, sir,
mm,
these are scanning electron microscopic images. These images are I just got by paying only, sir. So that's why I'm having a limited number of
I got it. So
images.
then you can take in patches and you can do it. What is the dimension of these images?
It is having 512 cross 512, sir.
Okay. Then you take the augmentation. Augmentation will be the another way.
Sir, particularly in augmentation, how to increase the number of images, sir? We can set parameters in coding or else how to
There is a
increase
coding
them.
is there. Augmentation coding is there. Shukla, can you?
Okay,
So
okay,
you
sir.
can perform any of the augmentation techniques. There are a lot of repositories available. There are flipping,
Oh,
horizontal. The same image is transformed into this many types of,
yes. Okay,
right?
okay, sir.
No
Yes, sir.
issue. Okay.
Okay, okay, sir. Thank you. Sir, could you suggest me particular task of limited data sets which I am having? Any CNN image classification model? Would you suggest anyone, sir, for a
Sir,
low number of data sets?
Sir, actually, it depends on the you have to experiment on the backbone network. So, what are the pretend networks available? That is DenseNet, RaceNet, or EfficientNet. You have to try it with your images, right? Feed it to the model and try to retrain the model and see the performance. Then you will able to decide that which backbone networks to further refinement is
Okay,
required. Okay.
okay. Thank you, thank you, thank you.
Already this collab code is given in the collab, so you can download it. You can check it. Already I shared this my PPT with your provisor. The provisor will share your PPT, then you can get the collab link.
Okay, sir. Thank you.
Okay. Okay.
Any other queries?
Okay, Dr. Pabi.
Thank you very much, Professor Anup Kumar Paul, for an enlightening session on anomaly segmentation in brain MR images. Has given us valuable insights into the practical application of deep learning in medical imaging. The clarity of concept, along with your rich research experience, has truly inspired us and added great value to this FDP. We are grateful for the time, effort, and valuable contribution to you to this program. Thank you, sir.
Thank you. Thank you. Thank you. Thank you, Dr. Pavi, for inviting me for these occasions. Okay. So I'm leaving the session. Okay. Thank you.
Yes, sir. Good evening. Deepa here. Sir, am I audible and clear?
Yes, ma'am.
Yeah.
Good evening, everyone. It is my privilege to introduce Dr. S. N. Deepa, Associate Professor in the Department of Electrical Engineering at the National Institute of Technology, Calicut, Kerala. Dr. Deepa obtained her BE in Electrical and Electronics Engineering from the Government College of Technology, Coimbatore in 1999. She pursued her ME in Control System from the PSG College of Technology, Coimbatore in 2004 and was awarded her PhD in Electrical Engineering from the same institution in 2008. With a strong academic foundation, Dr. Deepa has developed expertise in control system, artificial intelligence, machine learning, and deep learning application in engineering. She has guided several PhD scholars in this area, contributing to the growth of advanced research in intelligent control and computational techniques. Her research work is widely recognized with over 175 research papers published in reputed international journals, conference and book chapters. She is also actively engaged in collaborative projects focusing on renewable energy, forecasting, neural network, and system identification. Dr. Deepa is a passionate academician and researcher who has continuously contributed to the academic community through teaching, publication, supervision of doctoral theses, and participation in professional bodies. Her work reflects a perfect balance of theory and application, inspiring students and fellow researchers alike. We are honored to have Dr. S. N. Deepa with us
Yes.
today, and we look forward to her insightful contribution in this session.
Yes, that was nice, Dr. Abhishek Mishra, for your introduction. So I'd like to just say a good evening to Dr. Prabira Kumar Shetty, who has taken all initiatives to bring us and connect us for this Atal FTP. So without taking much of the time, let me go into the topic. So I think I have given the topic as for better clarity. I think I will switch off my video. Sir, is that fine, Dr. Prabira Kumar?
Yes, madam, no problem.
Yeah. Thank you. Let me give the insight of. So I have given my topic. My session is to be on. I think deep learning models for lung cancer I have given. So I don't know the code I have taken, whether it will be running for lung cancer or brain tumor, whatever it is, because the session is only 1.5 hours. I will try to cover maximum what is feasible so that you can take it forward and implement for your research works or for your thesis, but whoever is being attending. I think somewhere the voice is getting echo. You can mute it. Anyone, someone is on. I think, I don't know. Let me find who is it. Yeah, someone. I think Pradeepa. Yeah, Pradeepa can mute it. Yeah, done. Yeah, see, earlier, see, always, whether it is AI, whether it is going to be computational intelligence. 1 minute, let me increase the thickness. Yeah. Yeah, this is fine. See, whether it is going to be your AI models with search algorithms and knowledge representations, or whether it is going to be ML models, or whether it is going to be DL models. I think this workshop is more towards this Atal FTP is more towards medtech applications. See, application you can apply it for anything. See, like I work on healthcare, I work on precision agriculture. I work on more, I love energy, green energy, clean energy, renewable energy, which makes me work more on wind, solar. Now that I have started with hydrogen as such, but my passion towards medical, it's out of interest, healthcare. When I learned all these models, I wanted to apply in different areas. So hence a different transformations and different level of how it would be feasible has got over the years, over the decades. I would specify it like that. So let me start with some mathematics and why AI, why ML, and why DL. If with this foundation you can learn any hardcore deep learning models or ML models. See why nowadays they are calling it as deep learning revolution. So I would like to introduce you like that. The deep learning revolution. Why this deep learning has become a revolution? Because see, when you get a phone, when you get your phone, a new phone, when you get a phone, what happens? So there are no images, zero images. Okay, so at the end morning you've got the phone. At the end of evening, you will at least minimum have 10 images in your phone, photos, some videos in your phone. The next day, minimum 20 images extra added, 30 images. 1 month, if you see a minimum of what, for example, 10 images per day, 30 days, if you take, so your images in your phone will be 300 images for a month, averaging a 10 images per day, or even 5 images if you take also, this will go to 150 images per day. Videos, how many videos, how many images we are handling. So just I am telling, with respect to your phone, you're a normal, we are an academician, we are a student, we are a MTech scholar, we are a PhD scholar. Our phones, we will have so much images. So think of media people, so think of like artists, think of like drones who are working. So think of like people who are working in GIS system, so etc., where their vital role is to work on images. So everywhere the images is getting the utility of the images is getting increased. And with respect to medical, see, medical, it is out of the hands. Medical is becoming a great revolution. So all your MRI, whether it is going to be a DICOM images, all your ultrasound images, etc., all that slices, etc., so much volumes of images. So I can show you few before going into what is that uh, before going into the depth, so you will be able to visualize. 1 minute. Yeah, so please see these. These are lung images. So these are lung images. So this is like patient 1 ka.
Actually, question dita pura bhala sahaja sahaja dita question.
So this is going to be like patient 2. This is for patient 3. So just feel the image size. So if you take even my laptop, I apart from this, I even have like tongue images. I can show you. Like this is one of the work of one of my scholar. So another scholar, if you take like yeah, this is all MATLAB program, Python codes. Yeah, tongue images. Yeah, this is your tongue images. This is based on tongue images, whether detecting you will have. This is fully your LSTM models, your LSTM models and BiLSTM models and GRU, everything. So see the tongue images. So my laptop, if you take, I have so much images. I have so many brain tumor images. I have these tongue images for detecting the diabetics of the patients. I have lung images, as I have shown. So the lung images, so like what to say, uh, yeah, this, yeah, because I'll open and keep, because I'll be explaining this lung, because I have given this in my title actually. So these are lung images. So now I want you to make you visualize the importance of all these images. So whether it is going to be a medical images, whether it is going to be a agriculture based images, etc., etc. So it is going to hardcore increase. See, for example, if you see this image, can you tell what are the features? How much are you? Anyone, please, not please just get back to me because I'm not able to see the other screen. Kindly, please see carefully these images. Can you tell the objects which are embedded in this image? Anyone, please respond. Traffic lights are seen?
Yes, ma'am.
Yes?
Traffic lights
Yes, yeah.
or
Hmm.
Yes,
buildings,
ma'am.
traffic
Hmm.
lights.
Persons are there.
Hmm. Yeah. How many images, how many different types of objects are there in that, including humans? Windows, flags,
Yes, ma'am.
lights. How
Pedestrian.
many are there? Pedestrians, each one like woolen there wears yellow color cars, white color cars. How many images, how many objects and how many features are embedded in this image?
Multiple.
Multiple. Perfect. I want this answer. See, a small image, it's like a road pathway, it's a zebra crossing. But when you take a picture from that, you could visualize so much informations are being embedded. Yes, I want to know which car is crossing with the rule and which is violating the rule. I want to take a camera recording. If I see, I have to capture all these, so much images. Now see this image. This image reflects a particular object. This image, all are same, all are lamps, okay, but each one has a lot of variations. There is color variations, there is shape variations, there is shadow variations, there is trees, there is hanging the different heights as it go. See the end what to say, end lamp, if you see the shadow is there, that blurriness is there. Okay, so this images, so now see how beautiful this image is. See how are every lights lantern same? Is every lanterns in this image same? Yes
No.
or no?
No,
No.
ma'am. No.
Yeah. I want to capture this. I want to capture. See, when it is going to be a, like a media, or when you are going to work in this, I want to be accurate. See, we are professionals, we are engineers basically, and we want everything to be like perfect. So see this images. So it goes on and on. A referee doing this. There should be no where it is open goal. Each time they replay the crickets. The footballs. Now to see, this is very pretty. A kidka. So see how many images are there. Can I tell a 3-year kid this is zebra, black and white? This is zebra. If you tell in words, will that kid understand? Yes or no?
No, ma'am.
No, yeah, I can't tell a 3-year kid, a 4-year kid, what is black and white. It is so tall, it will have a tail at the bottom. You don't know what is tail. You don't know what is black and white. The 3-year child don't know which is white, which is black, which is blue, which is green. Everything is images. That too with his like past 15 years with his gadgets, everything is images, everything is going to be videos. So hence what happens, so see, I want you to see, however the cat is, and everyone are not waiting. See, you do Google, you do Chat GPT. Will you wait for 1 minute for your answers to come back by the search engine? Will you wait for 1 minute?
No, madam.
Yeah, you can't wait, right? You give it to Google or you give it to ChatGPT. Okay, so whatever it is, what happens? You wait for a nanosecond, you wait for a microsecond, you want it to return, right? You wanted to give the output. Yes or no? We can't wait 1 minute. Will we be sitting? Even if you want some diagram from ChatGPT, it will take analyzing. If it is doing, we are losing patience. Again, you will close the ChatGPT, open in another version. So this is normal. Okay. So hence, what happens? So the handling of images is very important, and what to say, you have to extract the prominent information from the images, as this is a medical, as this is going to be a medical FDP. Let us speak about medical applications itself. So lung itself we can speak. So when the lung is going to be there, so if here is going to be the tumor part, so if this is your lung partition, so like this, and this is your lung partition. So if the tumor is somewhere, if it is going to be like this, so not what happen now, I am able to see the images, a CT, computer tomography. So your CT images are there. So so your CT images will be there. So in case MRI is required, they will go for magnetic resonance imaging as well. So in this scenario, I want to know all the informations. So I want to know all each and every image informations. So now why this deep learning revolution came? See, if deep learning revolution is not there, because my title is deep learning and CNN, etc. something. So let me speak. I don't know how many speakers have spoken, but even then, I want to give an explanation in my perspective. So if you see, if DL is not there, you forget DL is not there. So now I have, so you will ask, there is always a question, ma'am, if DL is not there, can't we do anything with the images? Yeah, you can do. Yes, yes, possibility 1 or 0, 1, you can do it. So how, so all the images is going to be there, the input image. So for example, here it is given for a cat image, for example. Yeah, this is your cat image. So here, instead of a cat image, we'll be having a lung image, for example. So this image is going to be there. If it is going to be a binary class, I want it as a classification. Like I want first as a regression whether tumor is there or not. Then it is regression. 1 or 0. Tumor is there, lung tumor or lung cancer is there, 1. Lung cancer is not there, 0. Then I go for classification. If tumor is there, what is the type? Type 1 disease, type 2 disease, type 3 disease. So that will be binary class. So binary class, whether tumor is there or not. Okay, so you have to work whether you're going to operate on a regressor model, predictor model, or you're going to work on a classifier model. When it is going to be multi-class, it is going to be, yes, tumor is located, what type of tumor, so like that it will go. So if I want to do whether tumor is there or not, if I want to classify type 1 tumor, type 2 tumor, type 3 tumor, etc., first I want to know this images. So first I wanted to know, let me open plain sheets actually. Um, yep. So see, for example, so this is going to be the image. So it is going to be the image. So this is lung image or whatever it is going to be. So now what happens here? So I will be dividing it into 4 by 4. I'll be dividing into 4 by 4. So 1 comma 1 pixel, 1 comma 2, 1 comma 3, 1 comma 4, 2 comma 1, 2 comma 2, 2 comma 3, 2 comma 3 comma 1. So now this is, so wherever this red part is there, wherever this red part is there, it is 1. Wherever red part is not there, it is 0. So this is how you form 1, 1, 1. Here it is there 1. Here it is there 1, 1. Here it is not there 0. Here it is not there 0, 1, 1, 0. So you form a 16 input based on your pixel values. So 1, 0, 0, 0, etc., etc. I'm not making it lack of time. So 1, 1, 0. This is your input decoded vector. So likewise, whether it is going to be medical images, whether it is going to be face images, whether it is going to be a plant images, whether it is going to be a cat, lion, etc., whatever is going to be the images, first the images will be into 3 by 3, 4 by 4, 1256 by 256, 1024 by 24. So you can learn this all in image processing. 1024 also, or 256 by 256. Based on that, then you will form this. So if I want to detect that as a flower, I have to extract something called features. I have to extract something called features. So this word is very, very important. Deep learning. In deep learning, you should know what is this word. The difference between the machine learning, and the deep learning lies based on this features. If this features process is done in both are same. This features process makes DL different and more better and faster and handle more number of images than machine learning models, because machine learning can act as a classifier. So your DL is also a classifier, but additionally it does something. DL is also a classifier, a regressor. Apart from that, it has one more additional feature that makes a DL different from an ML. So now I am telling, so image is there. Now I am telling the image is there, and for performing operation or performing classifying this image, this as a flower or not, I need to extract. Flower means 1, not means 0, binary class. So I have to extract its features. What was the fundamental earlier? Okay, not earlier, always, which is versatile, which is always not going to change, is your transforms, which is not at all going to. I have my images, so in my phone so many images are there, so many medical images are there. I have to handle this. Take the images, apply the transforms. Why do you apply the transforms? What madam you are telling about transforms? Okay, so discrete cosine transform, Fourier transform, discrete Fourier transform, wavelet transform. Why are we using these transforms? Because I have this pixel values are there. I want to extract the prominent features from this thing. I want to do the images, whatever I have images are there. All these images, whatever I take, whether it is medical or something, it will have noises. So these noises, I have to work on these noises and I have to remove these noises. So wherein I have to do the pre-processing step to remove the noise or eliminate. So for that, I need to have so many filters. Okay, so Butterworth filters, low pass filters, high pass filters, band pass filters, band reject filters. So any type of filters. After the image pre-processing or filtering is done, then I have to extract the features. See, our face is there. So our face is there. So right. So your face is there. Okay. So always, which is your prominent? They tell T joint. What is this T joint? So two eyes and your nose, your mouth. Okay. So this is your T joint. Okay, so this is your T joint. So they will always your hair. So see this is going to be your T joint. So you will be identified by your T joint. So just you think eyes together, your nose, this is called as a T joint. So this is your T joint. So when you are recognizing some face, some teeth are there. Okay, some teeth are there. I want to recognize the teeth. So which will be the prominent? See, cheeks. In cheeks, nothing is going to be there. What is there? Everyone's cheeks will be same. No scar, nothing. If scar is there, at least if the teeth is going to have a scar, are, it is fine. I want to capture in the way the distance between the eyes, the nose, the size of the nose, the size of the mouth, whether the face size is this. So which will give a if face recognition and face classification. So this T joint, so the features will be extracted from the T joint. So likewise, every images. So whether it is going to be your lung images. So this is going to be your lung images if you take. So see this. This is going to be your lung images. It will have, if there is a tumor. So see, this is lung in different positions. So this is your lung. So if you see small white color, these are all called nodules, lung nodules. These are not lung cancers, nodules. So see, so this type of lung is like fully some. It is like what to say, like they tell it is being occupied. Still it is, there is no space. Still these type will need more breathing is required. They need an what is a respiratory support like this if the lungs is fully covered with all this. So there are many aspects this. So everything will have a feature. So I wanted to convey you like how T joint, every images like a brain tumor images. For example, yeah, I think this is again lung. Yeah, so if you see, this is a brain tumor. So see, the white part is going to be the brain tumors. This white part is going to be the brain tumors. I want to mask everything. I want only the tumor to be captured. And after the tumor is captured, I wanted to set as whether it is a type 1 disease, type 2 disease, type 3. See, this white color part is alone a tumor. So hence what happens here, after the images, filtering is done. So filters, band pass, band reject, high pass, low pass, basic filters. Let's not go to Butterworth, etc. So feature extraction. All these features are being extracted by means of transforms. Let it be Fourier transform, let it be discrete cosine transform, let it be discrete wavelet transform. So any transforms. After the features are extracted, so that will be again a 4x4 pixel where prominent features alone will have one. If it is not a feature, it will be 0. The rest all will be this. After this feature extraction, so you would have heard, if you're few faculty members, if you're working, you would have heard something word like run length matrices. You would have heard like GLCM. If it is going to be like if it is going to be brain tumor, like gray level concurrence matrices. So GLCM features, RLM, run length matrices. So these are some of the features, skewness, kurtosis, etc. So many are there, my dear friends. You can just Google or ChatGPT. So whatever you're comfortable with, you can find all those. So after the features, prominent features, I will not tell all the features are extracted. After the prominent features, because once the prominent features are extracted, these prominent features are going to decide these prominent features are extracted. These are going to be given into the classifier model. These are going to be given into the classifier model. So this classifier model is your computational intelligent model or soft computing model or your machine learning model. So machine learning as a classifier, regressor, linear regression, logistic regression, clustering, k-means clustering, any type of classifier, neural network, like back propagation neural network, radial basis function neural network, etc. So then here you will have your neural network models. So like how if you see here, this is a neural network model. So even this will be a your deep neural network model also. So this features extracted one like this, it will be given to the neural network model and output will be class 1. If it is class 1, for example, it is type 1 disease. If it is going to be class 2, it is going to be type 2 disease. So like that it will go. Now where our DL comes. So if I am going to have machine learning, if I am going to use, so whoever are known of it, no problem, but few who are not known of it, this will give you an overlap. So first images are there. So pre-processing, filtering plus etc. Feature extraction. Then comes your ML model. Then comes your final output. ML ka output is your classified output. Your classified output. Now with the growing data, I don't have all time to create run length matrices. I don't have all time to create GLCM. What are these GLCM features? These are features like mathematical notation. See, I said features means T joint, but if you write it in mathematical form, it will be some values: skewness, kurtosis, run length matrices like this. So the mathematical representation of this T joint features will be some keywords will be there. You can just know those keywords. So what happens here? So this features will be extracted, and then only before deep learning was there, before deep learning was not into existence, they do this pre-process it feature. You see all older papers of any peer reviewed journal, referred journals, if you record, everything will be like this. We applied DCT, we used GLCM, we used wavelet transform, we extracted, then we designed on a VPN classifier, a perceptron classifier, a multi-layer classifier, and it goes. This will have its own training rules, gradient descent learning rule, etc., and the output goes. Now with the deep learning, everything is done by deep learning. You don't go for, when you have deep learning will do your pre-processing, it will act as a filter, it will remove the noise, it will act as a feature extractor, it will extract the prominent features. You need not go for DCT, or you need not go for DFT. Then it acts as a predictor, or it acts as a I don't know why it is. It acts as a predictor. It acts as a it acts as a predictor, or I don't know why this continuity is not there. It acts as a predictor, or it acts as a classifier, and it gives the classified output. So now this is the deep learning revolution. So in a deep learning, you don't want you don't want any other what to say, any other separate feature extractor. Nothing is required. Everything, it has few operations. So if I want to remove the noise, filtering is there, so filter kernels will be there, it will take place. If I want to catch the edge position, see for example, if I am taking a river, in between the river, what is not point, from where the river point starts, so my boundary is very very important, my boundary. So this is going to be river, fully this is going to be water, for example. So this is fully water, center is a river, I don't want to capture center portion. Okay, so what will happen? A geologist, if he wants to take only the edges. I want to capture the edges from where the boundary, where the this starts, so from where this starts, so hence I have to capture the boundary. So for that some operation is there. So for each and everything, image processing, image transforms, image based feature extraction, image filtering, all these are replaced by few operators, few operations. All are replaced by means of few operations, very simple few operations in deep learning. So this is deep learning. That's all. Now we can go into different types of models. We can go in for different types of models. So your clarity, if you want to work, see, I always love working with machine learning models. My favorite is support vector machine models. So still now your paper will get accepted if you work in SVMs. And SVMs, if your data, your image data, your medical image data, if it is going to be a imbalanced data, then imbalanced non-linear data, Okay, SVM kernel, there are different types of kernels. SVM will give you a better solution. So if I have love for SVM, I want to use only machine learning. I don't want to go for deep learning and make the system complex. I don't have a workstation. I don't want to go to Google Colab to work for deep learning because so many operations are there. Machine learning has simple operations. In my computer, my laptop will be sufficient. We run deep learning and our 2 laptops crashed because we were not having the capacity for so many millions of operations. It will take 3 days, it will be running. Like how earlier in 1999, 386 machine, 486 machine, a normal machine learning neural network will run for 3-4 days, 10 days. Now though deep learning is running in small laptops, but workstation or CDAC will give you a better solution. So if I want to work on SVM, if I want to work on SVM, then if the image is there, I have to use all your DCT, WT, extract the features, then I have to give it to SVM. See, still that is there. Just because what to say, just because since deep learning came, it does not mean it has replaced the machine learning model. Never. So if you want to work with ML, you have all pre-processing, feature extraction, then ML. Otherwise entire thing fully done by DL. That's all. So I think this has given you a clarity why you want to go for DL. Yes or no? Is it fine? Shall I proceed further? Any
Yes,
doubt?
ma'am. I have one more doubt, ma'am.
Sure.
If you want to detect that multiple objects means you can go for DL. If you particularly want to classify only 2 object means you can go for
ML.
machine learning. Is it correct, ma'am?
Yes, even that is correct. But more features you want to extract, and then also it is better to go for deep learning. Features. And
Okay.
I don't want to do image based operations. I don't want it to do image based operations actually. I don't want it to do image-based more operations like DCT, DFT, or wavelet transform. Like that pre-processing all, I don't want it to do. So I want an inbuilt for feature extraction as well as for classification. In that scenario, you can go for DL. So whatever you said is also correct. If it is going to be a very small class, one class like binary class, you can go for ML models. When you want to have a different multi-class or a multi-labeled classification, you can go for deep learning. Along with that, if I don't want to go for a separate filtering, separate feature extraction, I want everything combined in one also, I can go for deep learning. Is that okay? Because deep learning will have a filter. Deep learning will have a feature extractor. Deep learning will have an edge detector by means of operations. But in an ML, you have to do everything separately. Are you able to catch?
Yes, ma'am. Yes, ma'am.
Yeah. So just to recollect it, whatever I said, I think it will be, you can recap it. Okay, so with this introduction of deep learning, so now so the most one of the prominent one which was chosen is which was operated was convolutional neural network. So I think I will go with the convolutional neural models. So I think that is, instead of going for all the slides, so this is your CNN slides. So let me take you through convolutional neural network. So which operation? So which operation performs? Which operation will perform your filtering? Will perform your filtering? Which operation will extract your features? Which operation will extract your features? So, and the corners, edges should not be lost. So edges. So this is one of the one of the very versatile deep learning model, CNN 16, CNN 32. So like that it goes. So I have operated more on CNN 16 and CNN 32. So this is for classification. So a cat has to be in what form, whatever form it is. See, this is a rusted car. This is not a new car. The cat is not like playing right, whatever it is. See, we are faculty members basically. Any type of student writes an a in any different form, our brain will be capable of classifying it as a. Yes or no? If he has written and in any way, what your brain does, and he writes in any way, he writes in like this. However, he writes, what your brain will do, what our faculty brain will do.
It will identify non-linear pattern also, ma'am.
Yeah, that is very, yes. However, he writes, okay, 32 pages car, 24 pages car, 12 pages car. So, however, he writes, you map. So, likewise, so however, this is a tree, however, this is a boat, whether it is the sea, a boat, a sky, here a sky is seen, a sea is seen, a beach is seen, a sky is seen. So, however, it has to identify. So, a CNN model, a CNN model, a CNN 16, one of the famous deep learning models, it is more suited for image classification applications. See, all the images will, as you all know, it will be RGB. So that is what is given. So red, green, and blue images. So these are all about image classification. So however this owl is there, so see this owl, however it is there, it has to classify. So instead of going for image classifications, whether it is like it is in different sizes, if it is deformed, it is like upside down. See, this owl is upside down, but my deep learning model or my ML model, it has to identify in what form it is deformed. It can be occluded. It look like a background. See, this is a tree. This is a tree. Inside a tree, this owl is sitting actually. So you don't know which is a tree, you don't know which is an owl, but your image classifier which you are designing should be capable. So see here, please see this image, a very beautiful image. So see here, so this is your tree. See, the owl is sitting here. Even from this image, your model should be a very good model. Whether a ML model or a DL model is a good model or a bad model, that is a very big research area. So here, so if you see, if you input this image to your trained DL model, it should recognize this as images. So like so I'm just skipping this image classification because I want to speak more on your what to say, our CNN model. So these are all linear image classifications, like normal ones before DL models. So these are neural networks based images. So now with all this convolution neural networks, so if you see convolutional neural networks, so they have, as I said, they will have filtering, they will have filtering, they will be having pre-process, what to say, extractor for feature extractor. So how they will form, and see, in machine learning models, if it is going to be a 3 by 3 dimension is there, I want to reduce this dimension, I can't handle this 3 by 3 dimension, I can't handle this 16 by 16 dimension, I want to do a dimensionality reduction, I wanted to do a dimensionality reduction, I have to go in for a machine learning model called principal component analysis. In any ML model, it does not include dimensionality reduction. See, all real-time practical data, your DICOM images, all will not be fully of, will be of dimensions, higher dimensions. Okay, so 3 by 3 dimensions, but I wanted to convert into a 2 by 2. So I want the dimension to decrease, because otherwise dimensions to be decreased, but the features should not be lost. See, very important words, whatever I am telling. Dimensions will be reduced, but features should not be lost. So image features, because these features are going to represent which class. So in that case, so what can I do with CNNs? What are they made up of? What are they made up of? See, a conventional neural network. So what is meant by MLP means a neural network before deep learning or before CNN. So a conventional neural network, it's a multi-layer perceptron. It will have lot of parameters to learn. It will have lot of parameters, so much. it is hard to make deeper networks. So there will be like a sparse connectivity. I'm not going to this connectivity. So what is meant by sparse connectivity all means? So like this, your model will be there. So it all should be connected to all. So, but what happens now? You can have sparse connectivity also. So sparse means few connections will not be there. Few connections will not be there. Only the important connections will be there. So which makes more influence? That connections alone. So from here, that's all. From here to here, it will not have here. So if you see this and this is there. If you see this, for example, this and this is there, that's all. So not all connections like this to this, this to this, this to this, full connections will not be there. So this is sparse connectivity. So like see, sparse connectivity is this is your dense connectivity. All inputs will have impact on all outputs. This is your normal networks. This is your normal neural networks, normal your backpropagation neural network, multi-layer perceptron, your Jordan Elmon networks, recurrent neural networks, everything will have all these things. On the other hand, if you see, local input has impact on local output alone. Enough. You make it local, you make it sparse connection. Why to have all? Why to connect everything and calculate? Okay, so here receptive, it is more this than only this. If you feel the features are here, you connect only this. If this is not at all connected, ignore this. So connectivities, see why everything is connection? Because our human brain has neurons. Our human brain has neurons. Each neurons, dendrites, soma, axons, etc. Is all the neurons floating separately? All the neurons floating separately, or how the neurons in our brain are? Hey, anyone please? Hey, anyone please? So how the neurons are in our brain?
Connected, man.
All are connected. It's a very simple question. See, everything is connected. The neurons are not like floating. Everything is going to be connected. Hence, whether it is a machine learning based neural network or a deep learning, these connections are there. Why connections? Madam, why connection should be there? Because based on the connections only, the connectivities will have strength, and that strength will be updated during the training process. And based on that connectivity strength, the output classification convergence will be obtained. You understand? So the output classification convergence will be obtained. So hence here, so we are not going into this weight solve. So I wanted to tell how the feature extraction is being done. So see here. So this is your filter. This is your filtering basis. What is it? This is going to be your filters. So what happens? This is your image. This is your input image. So for example, 4x4, I don't know whether it will have here. 8 minutes. I don't know, with examples I wanted to tell. Okay. Okay, so this is your, I'll explain with this itself, it is better. Okay, this I'll explain. So see, now in case of a separate ML classifier, what will happen is you need to have a separate band pass filter or a low pass filter, etc. Now, if you see, you are using a filter, you are going to use a filter or a feature map, for example. See, for example, I am taking here, for example, no, it will take it will take a large time. So I'll try explaining with this itself. See, this will be the size of the image. 1, 2, 3, 4, 5, 6, 6 by 6. So you will have 36. Now, so if it is going to be, this is going to be 6 by 6. Now here what happens, I am going to have a filter. What is meant by filter is, the filter size is, for example, going to be 3 by 3. Okay, so that's all. This is going to be 3 by 3. For example, 0, 1, 2, or 2, 2, 0, or for example, 0, 1, 2. Now, what I will do is, here there will be some values, 1, 1, 1, 2, 2, 2. So, pixel values, okay, 0, 2, 1, 3, 1, 6, so 1, 0, 0, this 1, 2, 3, so etc like this. So this is my input image. This is my input image. Okay, this is my input image. This is going to be my filter. Okay, this will be called as filter kernels. This will be called as filter kernels. So they call it as filter kernels. Now what should I do is, if I want to apply filtering, see, this is 3 by 3. So here also I should take 3 by 3. So 1 into 0, this 1 into 0 plus 1 into 1 plus 1 into 2 plus 0 into 2 plus this 4 into 2 plus each pixel values multiply by the filter values. Okay, put it in the first place. Next, take the next third. Okay, next 3 by 3, multiply it. Take the next one, multiply it. Take the next one, multiply it. So after this first row is over, now see how I am taking. Take this 3. Okay, take this 3, multiply by the filter kernel. Take this 3, multiply the filter kernel. Take this 3, multiply the filter kernel. After this is done, now you go. So here, so this 3, this 3. So what will happen? You have to multiply. You have to do the filtering of all this. So that is what, each like pixel by pixel. So this, then this. So see, they have not done. So first they have done here, and they have immediately gone for this position. Okay, from here, if you are taking here the stride, they call something called a stride. The stride is 1. But if you move, see, for example, if you have move this, then one, you move after 2 positions. You don't move 1 position, you move after 2 positions, then it is stride 2. If, for example, it is going to be stride 3, means you will take only this 3, 1, 2, 3 is over. You will take only this. Then you will take only this. If it is stride 3, okay, so stride 1. So multiply all this with this filter value. So just to forget this here. So just that filter values. So the filter size. See, the filter size can be 2 by 2. The filter size can be 3 by 3. The filter size can be 4 by 4. So when the filters are applied over the input image pixels directly, that is what it is here. This is your image, input image. This is your filter kernel. This is your filter kernel. So like how I said here, right? So 1 into 0, 1 into 1, 1 into 2. So multiply it, the value first you write it here. 100%, the size will reduce. The size will reduce. There are some formulas to calculate. If it is 6 by 6 input image, if the filter size is 3 by 3, if the filter size is 3 by 3, so how do you calculate the thing? So a formula is there. What is that formula? If you see, size of input minus size of kernel. Size of input is 6 minus size of kernel is going to be 3 divided by stride. I am moving stride 1 by 1. So I am taking like this, 1 plus 1. So 6 minus 3 is going to be 3. 3 by 1 plus 1. So 3 plus 1 is going to be 4. So after I apply this filter kernel on this input image, this 6 by 6 gets transformed into 4 by 4. Okay, you don't want a separate low pass filter. You don't want a separate high pass filter, band pass filter, band reject filter, Butterworth filter, Chebyshev filter. Nothing filters is required because if the pre-processing has to be done, then only you can give it to ML. In DL, you have this filtering by itself. So these are sample filter kernels. If you I use, see, like in cameras now, when you take photos, they tell, we don't know anything, our kids are far better. They'll tell, amma, use this filter, use that filter, use this filter. That is what is being done in deep learning. Basically, when you use that filter, however our face with all some minute things will go, and it will be a very big quality. A filter is being applied. If you take the features of these filters, it will be these kernel functions. So this is going to be your image. This is one of the filter kernel. So see this. So this is convolution. See, each one will have this type of values. So you have to. Any doubts? Okay. Each one will have its own different kernel functions. Okay, so this is your filter kernel. So see, this is also a filter. This is input image one. So they call, instead of filter kernels, they can also called as this operation. How you're telling this, each one being getting multiplied. This operation is called as convolution operation. This is the operation 1 into 0 plus 1 into 1 plus this is called as convolution operation. See, now you will ask, but what about the edges? I am missing the edges. Okay, so I am missing the edges in this case. So for edges, I want to use it like this. I'll take a different one and explain. Yeah, see here. So this is my image. This is my input image. See, this is my kernel function. 1, 2, 3, 4, 5, 6, 7, 8, 9. This is my kernel function, which is you're able to see in this slide. Okay, so now I want to capture. See here, in between only one is there, 5 by 5. Okay, so this is going to be 5 by 5. This is your image here. Okay, so now if I am going, why this padding is coming? See, 0 padded images. So convolution, what is meant by convolution? One image is there. This image you are multiplying with this 0 into 1 plus 2 into 0 plus 3 into 0 plus 4 into 0 plus 5 into the 0 plus this 0 into 6, 0 into 7 plus 0 into 8, 1 into 9. So if I am applying this kernel, so this first will be 9. Okay. Second, if I am applying this like this, so 0, 0, 0, all will be 0. I think you will get 8. Okay. So then I am applying this stride. So 0, 0, 0, I think it will be 9, 8, 7. Then I go for this. So like this, I do this kernel. Now what they have done is padding. So adding zeros here. Why these zeros are being added? So that the edge information is not lost. Because when you do without this padding, what will happen? This corner car will be participating only one time. But if you see the rest all, the second column is coming. See here. See the first column. If I am taking, why I am taking 3 by 3? Because my filter kernel is 3 by 3. If my filter kernel is 4 by 4, I will take a 4 by 4 here. Since my filter kernel is 3 by 3, I am taking a 3 by 3. So see here, first column is now coming one time. Now see, next I am applying the filter kernel. See the second column. Second column is, first column has come once. Second column is here for the first time. Now when I do this, now second column is participating in the second time. Third column has participated in this blue color also. Third column has participated in this red also. Now I am changing this. So third column is participating in green also. What happens? This third column features are being carried out for everything. For n number of times more than this first and more than the second. I want to give equal operation for each of these column images to have. Hence I am adding padding. Hence I am adding padding because edge features are not lost. Why padding in deep learning? Why filter kernels in deep learning? Using the filter kernels, you convolute this with this, you convolute and you find the output. After that, again you feel still the features are lost, again you convolute, again choose a different kernel, again you convolute, perform convolution. What is meant by convolution? Normal, multiply this 0 into 1 plus 0 into 2 plus this. Then again, if you feel edge is required, do padding. Why I should do padding? Because in order to facilitate all the features in these images are participating. So this is your zero padded images. So everywhere surrounded by zeros, so that you take all, so that no, see, this depends on the problem. See, machine learning or deep learning model, if I want always an accurate model, I wanted a good model, I don't want a bad model. So it depends on the problem, it depends on the data, it depends on the goal, in which you have to goal you have to reach. I want to my goal is to locate the cancer or not, to locate the tumor or not. No. My goal is to identify the cancer, and also it has to classify whether it's a type 1, type 2, type 3, etc. So hence what happens, it depends on which you have to choose. So hence, if padding is not required for your application, don't do padding. See, CNN, all this machine learning, DL are all heuristics. There is no hard and fast rules. All are heuristics. Very important. This word is very important. It's all heuristics in nature. Why it's heuristic in nature? Because if it is going to be low pass filter, I have to use that low pass filter. If it is going to be a band pass filter, I have to use. If it is going to be a discrete cosine transform, I have to use. Fourier transform, I have to use sigma. This is equal to that. I can't make that's our hard rules, because I have to apply what is in that formula for that. But deep learning, machine learning are all heuristics in nature. So hence, if I don't want padding for my application. Everything, see, like if it is going to be like this brain tumor, it is going to be in okay, something happened. Okay, so it is going to be in center. So I'm least bothered about the edges. I'm least bothered about the edges of this image which is seen here. So hence, in this case, I don't want here. Okay, so nothing is there front, I think. Okay, so see here, here also the brain tumor lies in center. I don't want to capture the edges. So hence, it is not at all required to capture the edges. So hence, convolution, filtering, filter kernels will be like this. This is a sample basically. There will be n number of filters. See, so much like Google Colab or Python program, so much has been like available in GitHubs and Kaggle.coms. So these are different types of filters. So see, this is one filter, this is one filter, this is one filter. Here I'm having 8 filters. You can use 12 filters, you can use n number of filters. So when I use this filter, my output, see, why 8? 1, 2, 3, 4, 5, 6, 7, 8 is here. Why 8 is there? 8 filters are being used. See, because this is 1 filter, 2 filter, 3 filter, 4 filter, 5, 6, 7, 8 filters are there. So each one is applied on these images. So it's actually a black and white, but it's here. If you see some operations, you might get this color variations also, or might be the color images. So this color image which is shown here, right? That blue color image. I don't know where it is. I think it will come after. This images, so like this it would have been used. So this is like a feature. So when I use this filter, I get this eyes nose. When I use this outer car, I get it. So when I use this I am getting this eyes. So when I use this, so see here, when I use this part I am getting. This part I am getting. When I use the sixth filter, I am getting outside something like this. So here I am getting dark patches. So each filters. So like how in your cameras you have your filters. So each filters, for each filters you apply convolution. You decide on the stride. You decide, that is very important. These words are very important. So stride means if you are moving 2 pixels away, if I move first, I am moving here, then 2 pixels I leave and I go like this, then it is stride 2. 2 pixels I move away, then it is stride 2. For example, here I am convoluting this with a filter kernel. So there should be a filter kernel. Both this multiply, that is called convolution. 1, 2, 3 I leave. This is going to be stride 3. So that depends. You have to choose more number of strides, what happens, some features may be lost. So hence maximum I have taken in all my works, try to be 1 or 2, not less than that. So color kernels input image, so 3 independent convolutions with the same kernel. So for R, for G, B, same kernels, each for 1. So like that you can use. So one color convolution, so everything will be in purple. So you can decide. See, once you use this kernels, you will get the feel of it. So see here, so this is going to be the same way, hence you are getting like frequencies. So you have to decide on which you have to use. That will come by like experience, like that you will come. So what is the neuroscientific basis of CNN? See, I always, in all my lectures, we think this has come in 2020s, or we think like it has come in like 2015s or something. So no. So this is actually neuroscientific basis of this is from 1959 and 1962, wherein based on this sketch. So there is some like video, you can search Google, just you put these authors, what to say, this author's names. So I think some disturbance, huh? Yeah. See, here you've seen this type of filters, right? So this type of filters. So here I have shown this type of filters. I don't know where. See this type of filters. So all are called GABA filters. All are called GABA filters. So initially I did not tell this name. So GABA filters. So that is what is given. So overall, mostly each of these GABA filters will have a special mathematical properties. So for your work, if you're working on medical images, so you can use this GABA filters. Each one, so here this will have pixel values 3 by 3 or 4 by 3, 1, 0, 1, minus 1, 0. Minus 1, 0, 0, 1. So like that, it will have its own pixel values. So these are various forms of GABA filters, which is mostly used in CNN models for best accuracy. So you can just have a note of this. Apart from CNS, so see, there are so much. So there were several groups. Like VGG group. What is meant by, you might have seen Google. If you do, you will find VGG net, visual geometry group. So this is called visual geometry group. So if you see, there is another net in CNN. So you have AlexNet. So another net, there is something called ImageNet. There is something called GoogleNet. So I will tell you each of these nets. So VGG net, VGG 16, VGG 32, AlexNet, ImageNet, GoogleNet, etc. So see, this is what I was teaching. So image is there, convolution. After the convolution is there, normal neural network, in order to obtain the output, you will be applying activation. So which are all the normal ones I have not covered, because this is generally in any ML, you will be applying an activation function. For example, a sigmoidal activation function, 1 by 1 plus e power minus x. So after this convolution, you get some value as 3 for each of the pixel values, 1 by 1 plus e to the power minus 3 if it is sigmoidal activation function. A Gaussian activation function, it will have e power minus x squared. Then you do pooling operation. So what is this pooling operation? That is, I have missed it. What is meant by pooling operation in a deep learning? See, CNN is one of the versatile deep learning model. Why madam is not talking? See, CNN is one. So many DL models are there. As I said, VGG, Visual Geometry Group, AlexNet, GoogleNet, ImageNet, LSTM, long short-term memory network, by LSTM, GRU, gated recurrent units, by GRU, transformers, self-connection, attention mechanism, etc., etc. It goes on day by day. Okay, so but all these operations remain same. At what time, at what, how many neurons are there makes the difference between each. Pooling, I have not said. What is meant by pooling? Okay, now see, for example, I am having, so I was telling somewhere the dimensionality has to be reduced, right? I was telling somewhere 1, 2, 3, 4, 5, 6, 7, 8. Okay, okay, 8, 7, 6, 5. 4, 3, 2, 1. For example, this is my this. What is my pooling operation? This is 4 by 4. This is 4 by 4. I want to reduce the dimension of this. I want to reduce my processor, or it is taking too much time. 16 by 16, 256 by 256, 1024 by 1024. It is taking a lot of time. So I cannot work with this. I want to reduce the dimensionality. I said in ML, if you want to reduce the dimensionality reduction, you will be going for principal component analysis. You will be going in for principal component analysis. So here, instead of principal component analysis, a deep learning model for dimensionality reduction has something called pooling operation. What is this pooling operation? Pooling operation, there is average pooling, max pooling, etc. Inverse, mirror, etc. is there. Here for simplicity, let me do what is meant by max pooling. See, first I take this 4. Okay. Next I take this 4. Next I take this 4. Next I take. Okay. Now what you do is Shrine. Okay. Now max pooling. 1, 2, 5, 6. The maximum value is 6, right? 6 here. 3, 4, 7, 8. The maximum value is 8 here. 8, 7, 4, 3. The maximum value is 8 here. 6, 5, 2, 1. The maximum value is 6. That's all. This is maximum pooling. A 4 by 4 dimension has been reduced into a 2 by 2 dimension. Max pooling into a 2 by 2 dimension max pooling. If it is going to be an average pooling, it is going to be an average pooling. 1 plus 2 plus 5 plus 6 divided by 4. 3 plus 4 plus 7 plus 8 divided by 4. 8 plus 7 plus 4 plus 3 divided by 4. 6 plus 5 plus 2 plus 1 divided by 4. So like this, it will be you will be defining. So this is pooling operation. So, but your principal component analysis for dimensionality reduction in ML model will be very, it will take its own. You have to calculate covariance. For all the covariance, like first you have to find an Euclidean distance or some other values. Then after that Euclidean distance, you calculate covariance, then standard deviation. Then based on some higher value, you have to take and do principal component analysis. So here, instead of all those operations, a very simple pooling operation will reduce the dimensionality. So CNN has filtering, CNN has feature extraction, CNN has edge detection by padding operations, CNN has pooling operation for what to say dimensionality reduction. So after this or then what happens, finally do all the operations, because each times, so you perform this n times, you perform this m times, you're not comfortable with the tumor identified or the cancer identified, whether it is an owl, the wood is also like that, the tree is also like that, the owl is also in same color, still the expected output is not coming. Again you do so much operations, so finally everything will be converted into a single decode vector. What is this called? A single decode vector. This decode vector or a decode feature vector will be given into a classifier model. So what is going to be a classifier model? Your neural network model. So your neural network with so many neurons are there, with your weights are there, fully connected weights are there. Then you apply your activation functions to determine the output. You'll be training, testing, and validating. Training performance, testing performance, and validation performance will be obtained. So this each one will be telling. So my original image size, since it is color image, it is by 3 by 3 by 3. 3 means for color image, so RGB. So 32, what I said, 32. So see here, I am doing my calculation. My input image size is 32. Size of the input minus size of the filter, 5 by 5 filter, divided by stride. I am taking the stride as 1. It is moving the pixels 1 plus 1. So 32 minus 5 is going to be 27. 27 by 1 plus 1. 27 plus 1, it is going to be 28. Hence, it is given here as 28. You're able to see, right? This is going to be 28. So this is the way. There are each and every step. There will be formula. Size of input minus size of strides minus size of the filter divided by the number of strides plus 1 will give you the, each time it will give you the size variation. Then if it goes through the pooling operation, you look which pooling operation, then 28 by 28 may get reduced into 14 by 14. So like that it goes, convolution stage. Okay. So see, this is your convenient. So like this we'll have, so 5 by 6 filters. So 28 minus 5 divided by, so 10 times the filtering is being done. So 10, 5 by 6 by 6 filters. So like this is your convolution stage. Activation stage, see, always you will be mostly using this activation function. This is called as ReLU. What is meant by ReLU? If you take rectified linear unit, RULU, this is mostly used, but all these are common ones. So sigmoidal activation function, tangential activation function, ReLU activation function, leaky ReLU activation function. So rectified linear unit. See, when during this much times of you're doing kernels, you're convoluting, you are padding, you're doing the operation. So what will happen if you see, it will become linear. So what happens? Classification will not take place. All will be 0, 0, 0, 0, 0. It will go to a saturation limit. So I want to introduce a non-linearity. I am introducing a non-linearity into the data, because over a time period, so this all you will know by experience. Okay, I am able to tell because we have got stuck up with that. So you have to add a non-linearity into the model. Okay, so that it does not abruptly hang. It will be running. You will never get the thing. So this is done by means of RULU, rectified linear unit, and leaky RULU. So these are some of the very important this. So pooling stage. So as I said, maximum pooling. See this orange color, 1156, maximum is 6. 2487, the maximum is 8. 3212, the maximum is 3. 1034, the maximum is 4. Okay, so average pooling, average of all these values. So your dimensionality, so a 2 by 2 filter and a stride 2. So a 2 after max pooling, you get this. 4 by 4 has reduced to 2 by 2. So this is your pooling on. So I have not said about all these dilated convolutions. So see, this is an architecture. So basic CNN architectures. So see, this is one of the architecture. This is LANET 5 architecture. The number of convolutions, the number of poolings, the number of filters, that only will be differing. Same thing, pooling, convolution, filters, padding. It will be repeated. It will be done in this is your AlexNet architecture. If you see this AlexNet, so max pooling is used, average is not used. So filtering is done, here filtering is done, here this, see finally your single, this is going to be 4096, this will be fed to the neural network model. Okay, so this goes like this. This is ImageNet. So how many layers are there? How many filters are there? So it goes. So as I said you, VGG, this is a visual geometry group. Okay, so if you see this, if you see this visual geometry group at Oxford University, okay, Simonian and Gisserman. So this is your Google Net. This is your Google network. This goes like this, residual network. This will have residual connections. So this is what which will be used in transformers. So your ChatGPT is your transformer, right? Okay, so generative AI and your transformer. So ChatGPT is a transformer basically. So ResNet models. So all this ResNet, etc. So accuracy, complexity, the tricks. Yeah, this is very important. The tricks of training a CNN model, whether it is going to be an AlexNet, whether it is going to be a GoogleNet or an ImageNet or etc. etc. You will perform data normalization. You have to initialize properly. You have to monitor the training process properly. You have to perform the hyperparameter tuning. So I think, see, this goes on because this was slides which was prepared for many things. So it was going on. Let me show you some implementation for this lung or the brain tumor. So this is your brain tumor. So this is in, I think I opened with a MATLAB environment, but this you can do it in Collab also. I don't know whether I have Collab for what to say, medical images or not. I'll just try to open in. No, I don't know. I don't know. I don't think this is in this ID. Okay, so Collab. Okay, I don't think that it will be there. That is Jupyter Collab ka thing. Okay, so let me explain here. I can share that coding if it is there with the organizers. So now, before the timing, let me do this actually. So this is, I'll just run this program. This is a basic MATLAB program. So this is like, for example, any brain tumor ka, let me try. Hopefully it should work. Yeah, see. This is a normal CNN model. So generic code MATLAB help you will get it. So this is your input image. This is your histogram equalization. So see how beautifully. So this is your input image, right? So here is your tumor. Here is your tumor. So your histogram equalization. Okay, so see now, though it is like binarized image, all black and white. The segment is done, and this is your final cutting. And if you see the command prompt, yeah, it will give you the type. See the command prompt at the end, please. Above the command prompt, I think you will be able to see my screen. The disease is of type 1 class 1. See the training. So it goes like this. So this is, I don't know whether for this, one second, I try to open. This is for training. I don't know. This is which image. Okay. Okay, so this is again, yeah, something. Let me try again. See, hopefully I got. See, sometimes it might not detect. See, hopefully here it is detected after running my program. Some cases it might not detect. Okay, so I think I can stop here. Any other things? Deep learning for computer vision. Yeah, this is like MATLAB framework. Deep learning. So there is in MATLAB, if you see all this, I'll tell you where is it actually. Yeah, see, this all will be there. You can click here like this image classification using pre-train. See, now though we have to use pre-train networks. Otherwise, our processor will go. So pre-trained models will be there till the final weights will be there. That weights you can take it and you can incorporate into this. So these are all like in MathWorks environment, how they're doing. So this is where we have learned from. See, there is local pre-trained networks. If you give AlexNet, if you give, for example, go to your command prompt like this. net is equal to AlexNet. Okay, so that package, I think this is 23 version. My 25 version will have. Okay, so 25 version will have here because it is not loaded. So, but this is about this car. So how everything is here. So this I have taken.
Madam, I think add-on is not installed. That
Yes.
Alexa add-on.
Yeah.
That
It
is
is
not installed actually.
that
Yes.
is what I'm not getting it. Huh? So I think so like only another 5 more minutes. I think I can open for queries. Any other queries?
Ma'am, I have one more query, ma'am.
Yeah, sure.
Ma'am, you said that a lot of different types of neural networks like CNN, then AlexNet, then
Yes.
like that. Each and
Image.
every neural networks are having the different convolution size and the coding size are there. Is it fixed, or if I prepare some other new network, means I can put the name in that net like that, because
Yes.
because how they are having the different types of models names and all, they are using different convolution layers, numbers, maximum police numbers, because how it is coming.
See, those are standards, sir. But now, see, for example, I was doing one project for our for in precision agriculture. There we used one CNN model, but we did not follow that because after following that, we were not able to. It was taking a lot of time, but time constraint. We have minimized the number of operation instead of a CNN 16. How much, for example, it is going to make, for example, 32 layers or something. We have reduced it to 10 layers. We performed the most essential. We selected the most prominent filters. When you select the most prominent filters, you don't do this edges, etc. You can modify the standard CNN to your requirement. That's all. There is no hard and fast rules. You have to follow the same CNN 16 or same CNN 32. Nothing like that. You can have your own filters. Even Gabor filters you don't want, you can replace the Gabor filters for that, so that features are being prominently identified. So that would be good actually. That is there. That is the answer to your question. Not necessary to form standard one. You can choose your own design, your own convolution, your own pooling. You can have your own limit the number of operations, and you can design your own proposed CNN models. That's all.
Thank you.
Yeah.
Excuse me, ma'am.
Yes, sure. Please.
I have I might sound silly,
No
but
problem.
there are different variations of CNN like LeanNet, AlexNet, ExceptionNet.
Yeah.
But whether these models differ by only the number of layers and number of convolution and pooling, or something extra, or some different logic is behind those networks.
First thing is number of layers, madam. Number of layers makes a lot of sense actually, because millions of operations will be performed. The number of layers matters rather than the operations, and the size of the filters, like 10 filters, 50 filters, 100 filters. See, nowadays the images are getting more complex, so you need more filters. So then only you can extract the prominent features, eliminating the noises. So the first thing is the number of layers. Second thing is the size of the filters. Third thing is the number of filters. So the spooling, convolution are based on the filters and the kernels and the strides which you use. So layers are very prominent. That decides the different types of nets. I have shown you now, like Google Net. So whichever I have shown you, you can see, like just Google and see images. AlexNet image, Google Net image, you will see all same words will be there, but the number of layers will be different. First difference lies in the number of layers. Architecture. See, always you remember any models, only three is very, very important. The first one is architecture. The second one is the activation function. The third one is the learning rule. So the architecture, the activation function, Gaussian, sigmoidal, ReLU. The third one is going to be the learning rule, whether it is going to be a gradient descent learning rule, how the learning happenings. So hence, if you see in all these cases, everything will be different based on layers. So that is the first difference for
So
all these.
if uh,
You can create your own layers also, ma'am.
okay, ma'am, thank you.
Yeah, sure.
Okay,
Madam,
so
you are
if
telling,
I'm able
madam,
to
Yeah.
madam, you are telling about that learning rule. That means alternatively you are trying to say that about the hyper parameter settings.
Sure, sir. See, here I have not at all touched about hyperparameters actually. Actually, hyperparameters is a very thing which has to give a very, what to say, key. It should be importance to be given to hyperparameters. So these hyperparameters play a major role in convergence of the networks. Convergence does not mean getting some results, getting a good result. Good. I'm not telling accurate result also. A good result. So hence, this hyperparameters are very important. Yes, using learning rules, the parameters like weight, bias will get adjusted. Apart from that, there will be like what to say, like learning rates. Several other metrics are there. So there is a separate topic for hyperparameter optimization itself.
Ma'am, can you please suggest any link or website where this mathematical background of these networks can be read?
Ma'am, I generally refer to MIT Coursera, ma'am. I have learned from MIT Coursera. So just go to MIT Coursera. So I think I forgot that name. In A it will start. He gives more on mathematical models. You check
Okay.
Andrew, I think. I don't know Andrew or some
Andrew and G lectures.
Lecture series. So go to MIT Coursera and please check that. That will help you behind the. See, everything is mathematics. It's not coding and everything. See how knowledge makes human intelligence, data makes machine intelligence. That's also everything is data. That too, if deep learning, medical images, you want image data. That's it. At the end of the day.
One more question, ma'am. That ReLU function, ReLU formula is if some value is greater than 0, that will be up to plus
Including
1. If
yes,
including 0.
yes, for including the non-linearity. Everyone will tell remove the non-linearity. But here you
Why
should.
it is called as non-linear? Because one is output is 2, it is plus 1 or 0. 2 output is there.
No.
So
When you work now, madam, you will understand because it will help in introducing a non-linearity to the data. When you see, it will be looking like that. Just you do hand calculation for like any inputs and see. In my website NIT Calicut, my my mail ID will be there. Even my phone number will be. You can just contact me also. You do it and you just mail me actually. You will see
okay.
it will be looking like plus 1 and 0 only, but actually it is not like that. That's what I'm telling. Only if you work out, you will have the feel of it. So it is for introducing non-linearity into the system.
It depends on the use and going into the more depth.
It depends on your data, your images.
Okay.
Yeah, someone
Thank you,
in
ma'am.
I think chats they have asked some this uh, some messages. Something I don't know. So something. Okay, so I'm not able to find any questions. Yeah, something. Okay, no questions. Okay, I think
No, madam, I think no questions. They
no
are
questions.
actually asking about the book. So I shared that book.
Oh, okay.
Okay,
Yeah.
that the author is good fellow. That book I already shared.
Okay, sir. Fine. That's I was. Good fellow. Yeah, good.
That
Yeah. Anything else? So I think if no other queries, sir, I would like to thank you, Dr. Prabira Kumar Sethi, who has been
yes,
contacting me. Very professionally, you were mailing me. So actually, I was held up actually because of all your mails. I don't want to deny it, and just for you, I have been for the session actually.
yes, ma'am.
So thank you for your.
Actually, I am searching that the professors who are working on my field on.
Oh,
Okay,
that's
like
very
that.
good. I
Yes.
will visit, sir. I was with IIT Bhubaneswar like last July. I came for Pectia 2025. I was in Odisha. I will visit Sambalpur University too. One
Okay.
day offline session. Huh?
Okay.
Sure.
Thank you, madam.
Huh?
Thank you
Dear
very much.
participants, thank you for your patience listening. Thank you. Thank you. Thank you all.
Thank you,
Yes.
madam.
Thank you, sir.
Recording stopped.